let's dive straight into the skeleton of the transformer architecture. Now, I know the classic diagram can look incredibly intimidating with all its dense boxes and overlapping arrows, but it's actually brilliantly simple when you strip it right down. What we're going to do in this explainer is map out exactly how this system works, from the basic plumbing all the way to the final output, without getting completely lost in the weeds. Ultimately, the entire transformer boils down to just 2 towers, and each tower is made of 6 identical blocks. Every single one of these blocks does exactly 2 things. First, it lets tokens look at each other. Then, it lets each token think on its own. That's really it. So, the absolute crucial point to keep in mind is that everything else we're going to map out today is just the plumbing designed to keep this basic 2-step process trainable. We can get a feel for the whole system by looking at these 2 main towers. On the left side, we have the encoder. It reads the entire input sequence at once, completely in parallel, to produce a really rich numerical understanding of it. You get 1 vector per token, and each token is now fully aware of all the others. Then, on the right side, we have the decoder. Think of this as the writer. It generates the output sequence just 1 token at a time. The encoder and decoder share a single connection, much like a translator, reading a whole text at once to fully understand it, and then a writer producing the translation word by word while constantly glancing over at the translator's notes. Now, that writer side, the decoder, operates using a process we call autoregressive. Autoregressive simply means that the model continually feeds its own previous output right back into itself to generate the next word in the sequence. It's essentially consuming the symbols it has already generated as extra input so it can figure out exactly what comes next. What's really fascinating here is the math underneath all of this, because everything inside a transformer is just matrix multiplication. Let's say we have a sentence of 6 tokens, and each token is represented by 512 features. Well, that sentence becomes a 6 by 512 matrix. When you multiply that by a 512 by 6 matrix, the inner dimensions just cancel out, leaving you with a 6 by 6 matrix. Watching these matrix inner dimensions cancel out is honestly the fastest way to understand what any layer is doing behind the scenes. A 6 by 6 result means you're looking directly at token-to-token relationships, where every single token is scored against every other token. Stepping inside that encoder tower, we find an exact repeating rhythm. There are exactly 2 sublayers here. First, tokens communicate like a committee in the multi-head self-attention step. They look around and gather relevant information from everywhere else in the sequence. Then, they completely stop mixing. Each token goes back to its own desk, so to speak, to process that gathered information completely alone, in what's called a position-wise feed-forward network. So it's look around, think alone, and then repeat that 6 times. To make that incredibly deep stack of layers trainable, the architecture uses something called an add step around each sublayer. This is a residual connection. A residual connection means you're adding a sublayer's newly calculated output directly to the original input rather than just replacing it. Think of it like editing a document with track changes turned on. The original text survives, and the layer just contributes a small edit. Crucially, this gives gradients, which are the signals used to update the model during training, a direct shortcut path backwards, and that prevents them from vanishing as they travel through the deep neural network. Right after that addition step sits the norm, or layer normalization step. Layer normalization just takes those newly added values and rescales them so they sit in a mathematically stable range. It normalizes each token completely independently, using its own mean and variance across its own features. These unassuming little plumbing steps around the sublayers are literally the only reason a deep model can train at all without losing its gradient signals. Because the sublayers only have to learn smaller corrections to what originally came in, and the gradients get a clear path backward through that residual addition, the whole architecture remains highly stable and capable of actually learning. And this brilliantly illustrates why a very specific number, 512, is so absolutely critical. The model's feature width, which is known as D_model, has to be exactly 512 everywhere. Why? Well, you simply cannot mathematically add 2 vectors together if they are different sizes. Since every single sublayer and embedding layer uses that residual addition, they must all uniformly output exactly 512 features to make the math work out. It is a strict structural requirement. Let's look a bit closer at that second sublayer, the feed-forward network. While attention decides what information tokens should have, the feed-forward network decides what to actually do with it.
It's a neural network that processes each token independently, temporarily expanding its feature width from 512 up to 2048, applying a ReLU nonlinearity, and then shrinking it right back down to 512. The exact same network is applied identically to every single position, with absolutely no cross-token mixing whatsoever. Now, surprisingly, this pretty unglamorous independent processing step actually holds roughly 2/3 of the total learned weights in every single layer. The attention mechanism uses about 1.05 million parameters per layer to gather information, but the feed-forward network uses over 2.1 million parameters just to process it. This entire two-step block, the attention, then the feed-forward, all wrapped up in those add and norm connections, is stacked exactly 6 times. Because each round starts directly from the enriched output of the previous layer, the model's representations grow progressively more abstract. The early layers capture surface patterns and nearby relationships, while the later layers tend to capture much deeper meaning and long-range dependencies. Moving over to the right side, the decoder tower, we see the structure is nearly identical, except for a few really vital tweaks. Its first step is masked multi-head self-attention. This means the decoder is allowed to attend to its own generated output so far, but a mask mathematically blocks it from seeing any positions that come after the current one. Without this mask, the model could just peek ahead at the future answers while training, which would completely ruin the learning process. So it can look backwards freely, but absolutely never forwards. The decoder also adds one crucial third sublayer, which is called cross-attention. This right here is the sole bridge between the two towers. Cross-attention is where the queries, which are the "what am I trying to write right now" signals, come from the decoder, and the keys and values, which represent the deep context of the input, come from the encoder. This bridge lets every decoder position freely look at every single input position to guide its translation. To finish the job, the final vectors coming out of the very top of the decoder stack pass through an output head. First, a linear layer projects those 512 wide vectors all the way up to the size of the entire vocabulary, say roughly 37,000 possible words. Then, a softmax function converts those raw mathematical scores into a token probability distribution. The model simply picks from that probability distribution to finally output its chosen word. While the original 2017 design used both of these towers for translation, most modern models actually split them apart depending on their specific tasks. If you exclusively need to understand a text all at once, like for classification or search, you use an encoder-only model, like BERT. If you exclusively need to generate text, you drop the encoder entirely and just use a decoder-only model. That gives us GPT and essentially every modern large language model today. Encoder-decoder pairs like T5 are really only still used when you need to seamlessly map one sequence directly to another. Modern implementations have also shifted some of the plumbing around. The original architecture put the layer normalization after the residual addition, setup called post-LN, but this required a really delicate warm-up schedule during early training just to prevent wild gradients. Modern models shift the normalization to happen inside the residual block, before each sublayer. This is called pre-LN, and it keeps gradients perfectly stable right from the absolute start of training, allowing us to drop the warm-up phase entirely. This architecture is so remarkably robust that vision transformers use the exact same base encoder tower to process images. Instead of using text tokens, it simply cuts a standard 224 by 224 image into a grid of 196 flattened 16 by 16 pixel patches. It projects them into vectors and runs them through the exact same stack of attention and feed-forward layers. Everything we just covered applies without any modification at all to computer vision. But all of this brings us to a rather massive structural loophole. If this entire incredible stack reads everything in parallel and attention treats all tokens exactly the same no matter where they sit in a sentence, how does the model actually know that the dog bit the man is not the man bit the dog? Since the architecture we've explored has absolutely no built-in sense of order, it leaves us with a fascinating puzzle about how it actually understands sequence and time, a puzzle that completely changes how we view the input.